and gentlemen. Okay, so we've kind of touched on some of this stuff already. A function is considered continuous. And let me back up a little bit. We have to talk about continuity in calculus for several reasons that we'll be getting into. The first thing is dealing with limits. Certain limits we have to talk about continuity with. For example, like the problem that we did with the where we had to find the limit from the left and the right and to determine continuity. That's part of it. The continuity also leads into the bigger two branches of calculus, derivatives and integrals. So this is like the foundation for the work that we do a little bit later on. But when we're talking about a function being continuous, this is pretty, when you think of something being continuous, you would think of it being unbroken, like something that continues on. There's not a break to it. There's no hole in it. That would be considered a type of breakage. Limit exists as x approaches c, which also leads into the graph being unbroken. All this is kind of connected. If there is no hole and the graph was unbroken, then the limit would exist. So these are kind of conditions that would have to be met. The limit as x approaches c of the function is f of c, meaning you can directly substitute. So limits where you can directly substitute, you can say the function would be continuous at that point because you're able to directly substitute. And then the fifth would be that there is a smooth curve or straight line. But if you were to actually look at the graph, there's not any visible breaks either.
So that's where the whole thing where 1 over x, that whole thing where it's just...
Like there's a break there. Yep. So we would say that function is not continuous because it would never meet.
No, I meant approaching from the right.
Yeah.
So that was continuous?
That part of the graph would be, yeah.
Yeah, well I was just talking about that problem specifically.
So absolute value functions are not smooth curves or lines.
They're straight lines. That would be still considered a continuous graph. There's no break.
Okay.
That doesn't stuff with that doesn't happen until we get into derivatives.
Yay.
So if you were to have like a quadrat, it'd be continuous?
Yes. All polynomial functions are continuous. Okay, if a function is continuous everywhere except at c, we would say the function has a, surprise, surprise, discontinuity at c. Some of this is pretty straightforward, but I do want to make sure that we're familiar with the way these are phrased, since you will have questions that ask you about discontinuity and continuity and all that. So definition of discontinuity, we've kind of already touched on this today too. You have two kinds. You have removable discontinuity, and you would have questions that ask you, is this removable or non-removable? But let's talk about what removable means. If you have removable discontinuity, that means that the graph is continuous at all points except one, meaning there's a hole in the graph. So if you were to look at the function, you would not see any major breaks or asymptotes or anything like that. You might just see a hole in the graph. And the other one is called, surprise, surprise, non-removable. They're not really fancy with these terms. Yeah, which makes it nice because it's easy to remember. So non-removable discontinuity means that there is a break. So the graph is broken, meaning there might be an asymptote in play.
Can you fix it with super glue?
No. Or you just have a piecewise function. So it doesn't have to be an asymptote. You might just have an actual break, like we might have in a piecewise. Now, when you have removable discontinuity, this is why it's called removable. Well, I'll add that because it might help to go through this part at the bottom first. But there's a reason why it's called removable, and actually when we looked at that, the reason I wrote that question on the board, the x minus 2 over x plus 2 times x minus 2, is because the x minus 2 part is what we would be considered removable, because you're actually able to get rid of the problem, and then the problem we couldn't get rid of is the non-removable. So is it possible to rewrite the function so it is continuous? Sometimes you're asked to discuss the continuity. So you have to look at the function you're given. You have to tell me, is it continuous? If not, does it have removable or non-removable? And there's ways to figure that out. So the first question, is it possible to rewrite it so it is continuous? If yes, then the function has removable discontinuity. That doesn't mean the discontinuity is gone completely. It just means now it's changed from an asymptote to just a hole in the graph, maybe. If no, then the function has non-removable. So removable might be a graph that looks like this but has a hole. Oops. So if you had a curve or something, a removable discontinuity curve would have a hole in the graph. A non-removable would be something that's actually broken. You can't remove the disconnect and change it to just a hole in the graph. There's an actual break. And then we'll come back up here to this little phrase here. Removable discontinuity when you're looking at a function. If you can factor or use a conjugate, so if you have a function and you can factor the function like we did on the board, or in some situations you can use the conjugate to simplify, then you might have removable. There's something you can do to try to simplify the function, like factoring a conjugate or flipping and multiplying two fractions, some of the stuff that we still use for limits, to simplify limits, then you might have a removable discontinuity. Okay. We're going to flip. Are you ready? Okay, let's look at two examples here. Of x equals x squared minus 1 over x plus 1. Okay. Now I can see one x value right away that if I was to graph this without trying to simplify it at all would be a problem. What x value is that?
1.
Negative 1, right? Because you can't have 0 on the bottom. So right now, I would have if I was to graph this by hand, I might have an asymptote at negative 1, because it would be something divided by 0. But to see if it's removable, this is where we try to factor it, try to cancel out the problem. Can I factor the top?
Yes.
I can.
Using differences first.
So I'd have x plus 1 times x minus 1 all over x plus 1, so what would cancel?
X plus 1.
Leaving you with x minus 1. This is just a linear function, isn't it?
Yep.
So the slope of this would be 1 over 1. The y-intercept would be negative 1. I can quickly graph that. Which is a straight line. But now, because I've been able to factor and cancel, my discontinuity, because we all agreed that I would have a discontinuity, has changed from an asymptote to a hole in the graph. Where is that hole in the graph?
Somewhere.
Negative 1.
Negative 1.
It's still at negative 1. but now it's a hole instead of a asymptote. So how you would show that on a graph is you would go to where x is -1, and you would put a hole at that spot in the line. So we know that with this particular function, I would still have a discontinuity, but it's the removable kind
Why do you
and not the non-removable.
why do you still have a hole there?
Because if I was to plug in -1 here, I still would get an undefined value at that spot.
But isn't your function effectively x minus 1, in which there is no hole?
Except you always look at your original function to determine discontinuity, not your simplified function. So the explanation, because this would be something that you would have to discuss, discussing it is more than just doing this problem and graphing. You would say that the function is continuous everywhere except where? -1.
We have to write this out every time.
It's asking you to discuss, yes. Really, you just have to make a continuous statement. This would qualify for the continuity statement. The function is continuous everywhere except blah blah blah.
Is it some type of little symbol like the therefore that means that entire sentence?
No, unfortunately not. Then you would have to describe what's happening at x equals -1. So at x equals -1, the function has what type of discontinuity? Removable. So you would say the function is continuous everywhere except where there's holes or asymptotes, and then you have to describe what's going on there at the graph. So at x equals -1, f of x has a removable discontinuity.
And it's removable if it's a straight line with no breaks.
It could be a curve with no breaks.
I mean just
Yeah.
like
A graph with no breaks. A graph with no asymptotes, basically. So f of x has a removable discontinuity, and I think that's all you need to say. Okay, so again, you have to make a continuity statement, and then you have to describe what kind of discontinuity you have. If I just had a straight line, if this was my original function, you could say the function is continuous everywhere, period. Like if there is no hole in the graph, there is no asymptote, you don't have to explain that further. Okay, the other one that I want to cover here trig function. We're just going to graph one cycle of this. So in radians, how long does it take to complete one cycle of the tangent function? 2 pi. So I'm going to mark 0 here. I'm going to mark 2 pi over here. Halfway in between would be pi. You have 1/2 pi and 3/2 pi. Okay, so I'm just marking some graphs here. This is not a tangent function that has any sort of transformations. So with a tangent function, where are the asymptotes located? 1/2 pi and 3/2 pi. Because remember, tangent is sine over cosine. Little trig review. And at 1/2 pi, you have the point 0, 1. And sine over cosine, or 1 over 0, would be undefined. So that's why we have an asymptote there. Same thing happens down here, except then it's -1 over 0. So that's why we have asymptotes at 1/2 pi and 3/2 pi. And the graph just kind of goes up. This is just a rough sketch, doesn't have to be beautiful. So that's the tangent function. With the graph. And then if you discuss the continuity, you have to make a continuity statement first. So we would say the function is continuous everywhere except, and then we'd have to fill that in. So we'd say, now you could probably simplify that. Instead of saying the function, you could say just f of x, if you want to shorten it up a little bit. F of x is continuous.
Can you write a little function for where the discontinuities are?
We are going to. Except x equals 1/2 pi plus pi n. because remember the tangent function goes on forever in each direction. So to show where all the asymptotes are, we take 1/2 pi, and if you add another pi, you get the next discontinuity. If you add another pi, you get the next one in both directions. Does that make sense? Okay. So you set up the continuity statement, and then we would say at those values, so at x equals 1/2 pi plus, we could say actually plus or minus, because you can go in either direction, plus or minus pi n.
Was that A plus or is that N?
Huh?
Where it says, because it say at X equals.
At x equals.
Okay, I didn't know if it was like A plus.
No. At x equals 1/2 pi plus or minus pi n, we would say f of x has what kind of discontinuity?
Non-removable.
Everybody else?
Non-removable.
Non-removable. Because can you simplify tangent at all to get rid of the problem?
No.
No, the problem is that cosine's on the bottom, so wherever cosine is 0, your function's going to have an asymptote. Can't really get rid of that. So we have a non-removable. Period. Okay? That's pretty much all you have to do for those. Star example 2. I think we'll come back to that one. And then I want you to flip. TJ, help me out here a little. Help me out. Alright, make an example 5. And example 6. You're going to the last page in that section, sorry. Under example 4, I want you to draw a line. We're going to do 2 problems like that one that we did for that packet. Actually, can I borrow?
Borrow it.
Never mind. I'll figure it out. Okay.
You can borrow something.
Oh, fine.
Okay.
Okay. So the directions would say find the value of c given the function 3x minus 2 if x is less than or equal to negative 3, 4c plus 1 if x is greater than or equal to negative 3. Okay, so this is very similar to one we kind of already did together. If you, find the value of c given this to make, that should be x, to make f of x continuous. If you get a continuity problem and you have a piecewise function like this and they want you to find the value of c, you always do it this way. I guarantee that you're going to have at least one problem like this on the AP exam, at least one like this on the unit exam, so this is something you can bank on. First thing that you would do is you would evaluate limits from the left and right, because you can see that the same, or both functions from the left and the right, they have the same breaking point of this negative 3. So we would find the limit as x approaches negative 3 from the left, and the limit as x approaches negative 3 from the right. What function is the function to the left of negative 3?
3x minus 2.
3x minus 2. Okay, so you throw that out there. And try your limit technique. So try directly substitute first. Does that work here? Can I plug in negative 3?
How do you, so the stuff where it says if x greater than less than the hyphen, are those two always going to be the same?
Yes.
Okay.
Okay, so I'm going to plug in negative 3. Yeah.
Can the answers be in fraction form, or do you want them in decimals?
They would probably take either. I would take decimals as long as it's rounded to 3 decimal places. Okay, so when I plug in negative 3 times 3 gives me negative 9, minus 2 gives me negative 11. If I plug in negative 3 into this other function, if I plug it in for x, I just get the expression 4c plus the negative 3, right?
Yep.
For c minus 3. So then your second step would be to set your limits equal to solve for c. So you'd have negative 11 equals 4c minus 3. If you add 3, you get negative 8. Right? Yep. And then your c would be negative 2. Again, going to the fact that in order for a function to be continuous, the limits from the left and the right have to be the same. So you're using that qualifier of continuity to actually solve this problem. So you're actually setting up limit problems yourself and making them equal each other. Yeah.
Aren't you, oh, never mind. You're adding to it, sorry.
Okay, I'm going to put up an example very similar to that. I want you to try that on your own. So same directions. Find value c. Given this function
If these two values here that you're writing down are different, like the x, like if they're different, like the 4 there, if it's different on the other one, can you do this?
no. They have to break at the same
So
spot.
then they have two different like limits that you're calculating.
Okay. Oh. The point in all that would be to make the function continuous. Okay, find your own, show all work please, and problem.
They probably give much harder than this stuff.
No, pretty straightforward. I mean, it's just remembering what to do if you're given this. I mean, the wording will be almost exactly the same.
Is it gonna be two-factorable fractions and
Not usually. Because, I mean, you can always directly substitute into the first one.
Because you're just
I mean, you're not going to have any weird stuff that you have to do
so are
usually.
you always gonna be able to direct substitute into
Everyone that I've done, yeah, you
into
can.
these kind of problems then?
Okay.
Never mind then.
For this one, the limit from the left would be the limit as x approaches 4 of this function. And when you plug in 4, you can directly substitute. You would get 12, right, as your limit value. Okay, so the limit of that would be 12. Here, evaluating the limit as x approaches 4 from the right would be that function. If we plugged in 4 there, you would get 32 plus c. So then you would take 12, set it equal to 32 plus c, so your c would be negative 20. That would be an
These are
option.
just way work.
Yeah, they're not bad. It's just knowing what to do if you get a hold of that problem. Okay, I think before we start talking about the intermediate value theorem, on just the front page of this, there will be one function that you have to write in this spot. So make sure that you and your partner, after you get your sheets, actually write it down. If you got your tangent partners, then quickly come get RLA.